On December 27th, 2004, something 50,000 light-years away, on the complete opposite side of our galaxy, physically disturbed Earth's atmosphere in 0.2 seconds, and almost nobody knows it happened. No earthquake, no solar flare, no asteroid, just a single pulse of energy from an object so extreme that physicists still argue about whether the math that describes it is even physically possible. That object is called a magnetar, and by the end of this video, you are going to understand why its existence should change how you think about the universe you live in, including what happens to ordinary atoms when they get close enough to one. Here is what you need to understand first. Space is full of dead stars. When a massive star runs out of fuel, it collapses under its own gravity and explodes in a supernova, one of the most violent events in the universe. What gets left behind depends on how massive the original star was. Some remnants become black holes, others become neutron stars, objects so dense that a single teaspoon of their material would weigh about 1 billion tons on Earth. To put that in perspective, if you took Manhattan Island and compressed it down to the size of a sugar cube, you would be approaching the density of a neutron star. Now here is where it gets extraordinary. Some neutron stars, a rare subset, are born with magnetic fields so powerful they break every intuition you have about what matter and energy can do. These are magnetars. And the one that reached out and touched Earth in 2004 is only the beginning of what we are going to cover today. Before this video ends, you are going to find out what happens to the atoms themselves, the basic building blocks of everything you can see and touch, inside a magnetic field this strong. The answer is something most physicists find deeply unsettling. Let us start with the neutron star itself, because without understanding what it is, the magnetar makes no sense. When a star between 8 and 20 times the mass of our Sun dies, its core collapses in under a second. The outer layers explode outward in a supernova. The core, now called a neutron star, is left behind. Compressed to roughly 20 kilometers across, that is the diameter of a city, but it contains more mass than our entire Sun. The gravity at the surface of a neutron star is about 200 billion times stronger than Earth's gravity. If you dropped a marshmallow onto a neutron star from 1 meter above the surface, it would hit with the energy of a nuclear bomb. Now, neutron stars spin fast. A newly formed neutron star can rotate hundreds of times per second, faster than a kitchen blender. And here is the key. A rotating electrically charged object generates a magnetic field. Neutron stars already have magnetic fields roughly 1 trillion times stronger than Earth's. But in a small fraction of cases, roughly 1 in 10 neutron stars, something happens during formation that cranks the magnetic field up by another factor of 1,000. The exact mechanism is still being studied, but the leading explanation from Duncan and Thomson's foundational 1992 research involves convection inside the star during the first seconds of its life. Violent churning of superhot material that amplifies the magnetic field the same way a dynamo amplifies an electrical current. The result is a magnetar, a magnetic field between 100 trillion and a quadrillion times stronger than Earth's. That field is so intense, it warps the fabric of space around the star. It creates what physicists call magnetic pressure, a physical force in the space surrounding the magnetar that can move matter without touching it. To give you a sense of scale, Earth's magnetic field is about 0.00005 Tesla. A standard hospital MRI machine runs at 1.5 to 3 Tesla. A magnetar's surface magnetic field reaches 100 billion Tesla. If a magnetar were placed where our moon is right now, its magnetic field would be strong enough to pull the iron from your blood before you could blink. If you did not know that, there is a lot more where that came from. Hit subscribe so you do not miss what is coming next. And that magnetic field is not just sitting there passively, it is actively shaping the star beneath it, building toward something that, in 2004, the entire planet felt. A neutron star's crust is not like the crust of the Earth. It is a crystalline lattice of atomic nuclei, iron and heavier elements compressed into a rigid structure, harder than any material that exists naturally on our planet. Think of it as the hardest, densest shell ever assembled, built from physics that operates at the absolute limit of what matter can sustain, but a magnetar's crust is under extraordinary stress. The magnetic field pulls in one direction, the star's internal pressure pulls in another. Over time, years, decades, centuries, this stress builds up in the crust the same way tectonic stress builds up along a geological fault line, and then the crust cracks. Physicists call this a starquake. When a section of the crystalline crust fractures and shifts, sometimes by less than a centimeter, the energy stored in that magnetic field is released instantly. Not gradually, instantly. On December 27, 2004, a magnetar called SGR 1806-20 experienced a starquake. The flare it produced released, in 0.2 seconds, more energy than our sun outputs in 250,000 years. That is not a typo. A fifth of a second, 250,000 years of solar output. The pulse of gamma radiation that exploded outward from SGR 1806-20 travelled across 50,000 light years of space and arrived at Earth, still strong enough to do measurable damage. It ionized, which means electrically charged, the upper layer of Earth's atmosphere, the ionosphere, at an altitude of about 85 kilometers. This is the same layer that reflects radio waves around the planet. Satellites designed to detect nuclear weapons tests registered the event. Radio communications were disrupted. The signal was so bright, it saturated the detectors on multiple spacecraft, meaning the instruments maxed out and could not record the full intensity. Scientists had to back-calculate the true energy output from what they could measure before saturation hit. Palmer and colleagues, publishing in Nature in 2005, confirmed the event was the brightest flash of electromagnetic radiation ever recorded from outside our solar system. Hurley and colleagues confirmed the ionospheric effects on Earth. Now think about that distance, 50,000 light years. If you travelled at the speed of light, 300,000 kilometers per second, it would take you 50,000 years to reach SGR 1806-20. And yet it still reached out and electrically disturbed the air above your head. If a magnetar of this type were located within 10 light years of Earth, there are currently no known magnetars that close. The same event would have stripped away the ozone layer. Life on the surface would not survive. And that still does not prepare you for what comes next, because we have not yet talked about what a magnetic field this strong actually does to the atoms themselves. Everything you can see and touch is made of atoms, and atoms have a structure you probably learned in school, a nucleus at the center, with electrons orbiting around it. Those electrons do not orbit in a random path. They occupy specific regions of space called orbitals, cloud-like zones defined by the balance between the electrical attraction of the nucleus pulling the electron inward and the quantum mechanical rules that govern how small objects move. That balance is what makes chemistry possible. It is what makes a water molecule stable. It is what makes DNA hold its shape. It is what makes you. Now put that atom inside a magnetar's magnetic field. In a magnetic field strong enough, and a magnetar's field qualifies by an enormous margin, the force exerted on the electron by the magnetic field overwhelms the force exerted by the nucleus. The electron can no longer orbit in its normal three-dimensional cloud. The magnetic force compresses the electron's path into a tight spiral, aligned with the direction of the magnetic field. The atom becomes elongated. It stretches along the field lines into a shape roughly 200 times longer than it is wide. Physicists call this magnetic confinement of the electron wave function. Dong Lai's landmark 2001 paper in Reviews of Modern Physics worked out the mathematics in full. Near a magnetar's surface, atoms are not spheres, they are needles. and needle-shaped atoms do not form the same chemical bonds as normal atoms. The chemistry that emerges on a magnetar's surface, water could not form in the same way. Organic molecules could not assemble. The periodic table of elements effectively becomes a different document, not too strong. The physical constants that govern how strong magnetic fields can become in normal space are set precisely enough to allow atoms to keep their shape everywhere, except the most extreme objects in the cosmos. Magnetars are not just violent. They are the universe showing you the edge of the conditions that make your existence possible, when the rules that hold everything together are pushed to their absolute limit, and they are out there right now. Here is what the 2004 event actually means when you put it all together. An object 50,000 light years away, with a magnetic field so strong it deforms the shape of atoms, released a fifth of a second of energy, and electrically disturbed Earth's atmosphere, not because it was aimed at us, not because it was close, but because the scale of energy involved was so incomprehensibly large that even after crossing the entire width of our galaxy, it was still powerful enough to affect our planet. There are approximately 30 known magnetars in our galaxy. There are likely thousands more we have not detected yet. Each one is a place where the ordinary rules that allow atoms to exist in their familiar form break down completely. The universe is vast, and most of it operates under conditions that would make chemistry, biology, and everything built from them impossible. The narrow band of conditions where stable atoms can exist, where electrons can orbit normally, magnetars are what exist just outside that band, and they are real. They are out there, and one of them already reached across half the galaxy and touched us. If this is the kind of thing you want to know more about, the science that most people never encounter, the discoveries that reshape how you see the universe, hit subscribe. There is a lot more where this came from,